Hey everyone, it's John Reed here from Learn to Stargaze. And I want to talk about something that really irks me about social media, and it's the incredibly simplistic math problems that are presented in an intentionally subjective way. You know the ones. No math teacher or textbook would ever formalize a math problem in this way. And that should be a red flag to disengage. But for some reason, folks can't help but post their answers in the comments, and the silly posts go viral. And there are two reasons I could think of why this is a huge problem. The first is that everyone who engages and sees answers that are different than theirs perceive the other people as stupid, just for seeing something in a different way. And I guarantee that 100% of the people who engage with the question and read the comments feel worse for having done so. The second problem is the reason why the shady math problem got posted in the first place. And my guess is that someone is data mining. They're trying to form a database of the kind of person who falls for these silly tests, and worse, the kind of person who argues themselves into believing something that may not be true. The person that's data mining probably believes that this set of people they've identified is easy to scam, and they become targets. So in this video, I want to contrast this with a different sort of problem. Problems I wish we saw more of, and that would actually make social media better. These problems use the exact same grade level of mathematics, 6th grade or 7th grade or something like that. And like the viral problems, there is an apparent subjectivity, but one that would lead to a healthy debate driven by curiosity and not adversity. In a moment, I'm going to attempt to solve a geometry puzzle, and you might think I've got the wrong answer. What's healthy about this type of problem is that I want to know if I'm wrong, and if I'm right, but I don't know why I'm right, I'd love to be shown why. A healthy problem should be legitimately challenging, and that doesn't mean you need to know any more math than a middle schooler. So here it is. My brother-in-law just sent me this puzzle, and I believe this can be traced back to a math teacher on Twitter named Catriona. It's called Setting Sun, Rising Moon, and the idea is that you have two half circles that both rest against the right side of a rectangle. A line tangent to the places where the circles meet bisects the rectangle. The goal is to determine the fraction of the rectangle that is shaded. Before I try solving this problem again, I want to point out that I definitely suffer with the problem of seeing only one way to get to a solution. I come up with a strategy, and I find it incredibly challenging to diverge from that strategy. Now, I'm sure there are far simpler ways to solve this problem, and if so, I'd love to see your solution in the comments. All right, so I actually have Aaron Nadler on the line here. Engineer, amateur astronomer, whiskey connoisseur, or scotch?
Any kind of whiskey.
Any kind of whiskey. Okay. Any other titles?
I guess that's those are probably the most pertinent ones.
So Aaron presented me with this problem, and he's got a much cleaner solution, but we're going to walk through mine, and I want him to test my assumptions along the way. And hopefully we can see what a healthy mathematical debate looks like. Okay, so let's start with the premise of the problem here. So let me get my pen going. All right, there it goes, engaged. We start with a rectangle, and it's bisected by a line. And what we want to know is what the area of the shaded part is. And so what I did is I labeled a side A, a side B, a length X, and a length Y. And so the fundamental goal of what we're trying to solve here is a fraction. So we've got this fraction, which is equal to, and I'll actually put the small part in the denominator this time. We've got
That makes me feel much better.
A times B, which is the whole rectangle, minus A times X over 2, which is the triangle, top, the area of the whole rectangle. Okay, which can be simplified by canceling all the A's and factoring out the 2, which gives 2b minus x over 2b. Okay? All right, so now the goal here, say our goal, which will solve the problem, we want to solve for x in terms of b. Agreed so far?
Yep, I'm on board.
All right. Okay. Now we need to bring these circles into play. So I'm going to draw the diagram again. And now here's where I'm making some assumptions that I don't know how to prove. And this is where it helps to have help or work on sort of puzzles, you know, with your friends, I guess, here.
I think we're friends.
Yeah, we're friends and family. Okay. So my first assumption here, you could say, ass number one, by inspection, it looks like the circle number one, which I'm calling the big circle, is twice the size of circle number two, or twice the radius. And so by inspection, you know, this line here, this green line down the middle, you know, bisects the center of the big circle and the side of the little circle, you know, which means that radius here, I'm going to call this radius 1 and radius 2. Okay. So, which means radius 1 equals 2 radius 2, and radius 2 therefore equals radius 1 over 2. Does that make sense so far? Is that a safe assumption? I don't know.
Yeah, it feels like it feels like the whole point is to not have those big assumptions.
But it's possible, given the geometry here, that could be proven.
Sure, yeah.
But I think
you have to prove it.
Yeah, I guess you would have to prove it, huh? But what's interesting is that the answer I get is clean.
Yeah.
Which usually is a sign that you've done something.
That you've made a good assumption.
Yeah.
Yeah.
Now what we want to do, because these problems are really only 6th or 7th grade geometry, we want to form triangles and use Pythagorean's theorem sort of all over the place to solve problems. So what we can do here, we can get, so we've got side B here, we can get side B in terms of R1, right? And so one thing we want to do before that is we've got this sort of hypotenuse here, which is equal to R1 plus R2. So we just want to know what that length is. So R1 plus R2 equals R1 plus R1 over 2 equals 3 over 2 R1. So 3 over 2 R1 is that hypotenuse. We know that this green line here is B, and we know that the radius of R2 is R1 over 2. So we scroll up here, I'll just write that in, R1 over 2. Okay. So if we want B in terms of R1, all we need to do is, you know, A squared plus B squared equals C squared. A squared plus B squared equals C squared, where A squared is R1 squared over 2, so that would be R1 squared over 4, plus B squared equals this 3 over 2 R1 all squared, which simplifies to 9 over 4 R squared. So B squared equals, did I screw something up here? 9 over, yeah, no, that's right. 4 R, oops, these are R1s, R1 squared minus R1 squared over 4 equals 2 R1 squared. Therefore, B equals root 2 R1. So assumption number 2 here, and this is where it got complicated for me. So let me draw this again. Ooh, my drawings are getting worse here. All right. So we know that this is a tangent line. Again, that's another assumption. I think that's a safe assumption, that this line is tangent to the circles where they meet, which means you've got 4 right angles here.
Mm-hmm.
And now we get to another assumption that I can make, but I can't prove. And that's, we want a relationship between X and B, right? So I'm going to form some other triangles here, triangle here, and a triangle here. And the assumption that I can't prove, but that seems right-ish, is that this in white is a right angle. And if that assumption is true, then we've got a B R1 over 2. We can create expressions with 2 variables and 2 unknowns that we could solve and figure out what X is, because we also know this length here, you know, is still whatever that is, 3 over 2 R1. So, and we also know that B equals X plus Y. And here we know that R1 plus, R1 squared plus Y squared equals A squared. It's from this triangle at the bottom. And we've got R1 over 4 squared plus X squared equals B squared. And then from the big triangle, we've got A squared plus B squared equals 3 over 2 R1. So just writing down what we see. And if I label these formulas, I guess this is where we get to more university algebra here, because we can add formulas together to solve for variables. So if we add formula 1 and formula 2 together, we get R1 squared plus R1 squared over 4 plus X squared plus Y squared plus A squared plus B squared. Oh, sorry, that's equals A squared plus B squared. And we can now replace A squared plus B squared with 3 over 2 R1. Let's do that. And let's simplify some things in here. So that would be 4 over 4, which is 5 over 4 R1 squared plus X squared plus Y squared equals, and that's 3 over 2. Oops, those are all squared. R1 squared. Simplified, we've got X squared plus Y squared equals 9 over 4 R1 squared minus 5 over 4 R1 squared simplified is X squared. It's funny, I leave a lot of stuff I think a lot of other people would do in their heads. And I think I skip steps that a lot of other people would do out, you know.
Yeah, it's always funny, like what people's like obvious moves in algebra are, and how other people's obvious moves are not the same.
I know. Okay, X squared plus Y squared equals R1 squared. And I feel like we could have got to that a lot earlier. Somehow. Okay. Anyway, so right now we've got an expression up here where B equals X plus Y. Therefore, Y equals X minus B. And so down here, we can go X squared plus, that's what did I say?
X minus
X.
B?
What was that? B minus X. No, X minus
B.
B. X minus B squared equals, oh, and I can get rid of that because B equals root 2r, which means that r1 equals b over root 2. And so we can go b squared over 2 here. Okay. And now do some simplifying. X squared plus, I always hate these, FOIL.
Oh, yeah.
X squared minus 2bx plus b squared.
I think that's right.
I hope, equals b squared over 2. And now this is a quadratic equation with 2 variables, but that's okay. So this will simplify to 2x squared minus 2bx plus b squared minus b squared over 2 is simply b over 2 on this side equals 0. Equation for a quadratic equation is x equals minus b plus or minus root of b squared minus 4ac over 2. And so in this case, we're going to divide, we're going to simplify the top one again to be x squared minus bx plus b over 4. And if we plug that into the quadratic equation, we get x equals positive b plus or minus root b squared, which is just going to be b squared minus 4, and then a is 1, c is that's squared, b squared over 4 all over 2. And we can see that it's just b squared minus b squared, so this term cancels. And x equals b over 2. And now we've got that relationship, fraction equals 2b minus x over 2b equals 2b minus.
You're on mute, dude.
How about now?
Gotcha.
I think the computer just got bored with my math. All right, so at least we're at the easy part here, and we'll just give this a quick or not so quick solve because I'm not super quick at this. 3 over 2b over 2b, which is 3 over 4 b's cancel. Okay, so my answer for what percentage of was shaded is 3 over 4. Now that's nice and clean. So here's what I want to know from you. Do you agree with my answer? Or did I make too many assumptions?
No, I think the answer, I agree with the answer, but yeah, I think you got to prove all your assumptions in this case. And that's where it gets sticky.
What could I have done better? I guess. Is there something I could do to improve my thinking about math in general that would help me here? Or was this just brute force? I stated my assumptions, which I think is good enough for a test.
Yeah. So, so this problem comes from a blog called Math with Bad Drawings. And a lot of times there's like some like slick rule that does this. And so my colleague, when he was solving this, was like, there's got to be something about lines intersecting circles and points.
Because there's got to be some law, I think, that makes this a right angle that I can't prove. And it also, I think this only works. This shape would only make this rectangle if those circles were half the size. Otherwise, like the lines just would go in weird places. Like if you try to resize the circles, it doesn't form that triangle. at the top that you're trying to subtract, if the circles are different sizes.
Interesting.
So it's, yeah.
So here, let me send you this message with the slick way, and if you want to, you could show it.
Okay. Wait a minute. So that's the end of the game, huh? So his rule is 2 lines that run tangential to a circle from a single point must be of equal length where they meet the circle.
Yep.
That's like a law, though. I guess the question would be, how do you prove that law?
Yeah, I mean, I think the thing is, like, you didn't prove.
Oh, that's it. I'm getting new internet. We just upgraded our internet to 350 MPS and put in Wi-Fi extenders, and I'm getting 3.7. 100 times slower.
Maybe Jen's streaming everything.
Probably. I think realistically, it's this new. I'm 3 stories up, and the extender's on the 2nd floor, and we just put in this hardwood floor, and I don't know what they use under the floor, like maybe like some tinfoil barrier.
Yeah.
Okay. So, what were you saying about my assumption?
Oh yeah. So it is one of those things. Like, if you just happen to know this rule, right? It's a sweet and easy problem. But you didn't prove Pythagorean theorem as a part of but you still used it, or you didn't prove. I guess you didn't use any like other geometric rules about sines or cosines, tangents, etc. But we'd sort of just accept that.
Yeah.
So, and I think that's like this slick approach, and it's so clean, and and it just does exactly what it does. Is one of those things, like, you just happen to know the right rule, right? It kind of changes the whole day.
I think that's one of those rules that I guess you would have to, like, you see Pythagorean theorem do its job all the time, whereas this one's more obscure. Yeah. So did you get a solution to this, or did you just cave?
No, yeah, I got close. I kind of did a visual thing, but I couldn't find this rule or I didn't think about the points and tangent lines and all that stuff. So I kind of knew it was 3/4, but I couldn't like rigorously prove it.
Mm-hmm. Yeah, well, I think I got it, but I'm still not confident. I would love like an internet debate of mathematicians to be like, you should have done this. So I'll be interested to see if I can salvage enough content here for a post, and who of my engineering followers, of which I have many, who are far better at math than I, including you, and see their commentary. And hopefully it's a much more valuable commentary than the commentary I see from some of the same people on math questions that are like 5 divided by 4 plus 3, where the brackets are in a weird spot,
Yeah.
All right. Well, thanks very much, Aaron. I'll let you get on with your day.
Later, dude.
And ciao. Thanks again.
Mm-hmm.
Well, that was a lot of fun. I just have one final point on the solution that Aaron provided. And the premise of that solution was that this line, and this line were all the same length. Well, early on when I was attempting this problem, I was wondering if one of the assumptions was that this line and this line were the same length. And so I actually got out a little ruler and measured it. And we can do that again here. And we can see that this line is 131 pixels here. And this line is 115 pixels. So to me, visually, the way this is drawn, these were not equal. So I didn't start with that premise, because that assumption would have saved me a lot of time. Now, mathematically, assuming this is tangent, I'm assuming that that's just an error in the drawing. And yes, this line and this line should be equal as well. But again, this just adds to the subjectivity in these problems, which definitely makes them a lot of fun. Well, I hope you enjoyed this video. Please follow me on YouTube at Learn to Stargaze. And remember, the future is looking up.